Okay, so we're going to work Chapter 5, Practice C, problem number 15. So as we always do, we're going to write our given and we're going to write our find. And when we read the problem, we're not going to read the whole thing at once because we're going to see there's a lot of information. We're going to chunk and we're going to write down one thing at a time. So it says a rock climber wears a 12 kilogram backpack. So in my given, when I write the 12 kilograms, if I'm not sure what that is describing the backpack, I look at the unit. This is kilograms. Kilogram measures mass, not weight. While scaling a cliff, after 30 minutes, so they're telling me the time is 30 minutes. Now, before I even go on and read the rest of the problem, I know I don't use minutes. We always use seconds. So what I'll do is I'll do that conversion right away in my given. So if I have minutes in the numerator, I put minutes in the denominator, and I know there's 60 seconds in 1 minute. So this minute cancels with that, and I end up with 60, and I don't even need my calculator. 6 times 3 is 18 and 2 zeros, so T is 1800 seconds. So again, I'm chunking. I'm reading, I'm writing, I'm reading, I'm writing. The climber is 8.2 meters above the starting point. So now I know that D is 8.2 meters. So A, how much work in joules is done on the backpack? So I want to find the work on the backpack. And I'm just putting subscript B for backpack. Well, we learned yesterday that work is equal to FD. Now, I don't have the force of the backpack. I have the mass. But I know that this force, because the backpack is being lifted vertically, the force is going to be the force of the weight, which we learned before is mg. So it's going to be mgd. So now I just need to substitute my values. So I have 12 kilograms times 9.8 meters per second squared times 8.2 meters. Now when I put the numbers in my calculator, I get 964.32. But let's look at the units. I have a kilogram meter per second squared. So a kilogram meter per second squared, that's a newton, times a meter, and I know a newton times a meter is a joule. So the work on the backpack is equal to 964 joules. So that's part A. Part B says if the climber weighs. So now they're telling me the weight of the climber. So I can call that FGC if I want. F of G is the weight. And then I put a double subscript just so I know that's the weight of the climber. So you notice here they gave me the weight and here they gave me the mass. And that's why I look at the unit. So the climber weighs 6.00 times 10 to the newtons. And now it says how much is the total work? Well, the total work is going to be the work on the backpack plus the work on the climber. But since I already did the backpack, what I'll do is I'll find the work of the climber and then I'll add them together for the total work. So the work of the climber is going to be his weight times, again, the same vertical displacement. So 6.00 times 10 to the 2 newtons times 8.2 meters. So when on my calculator, I'll get 4920 joules. But now they want the total work. So again, the total is going to be the work of the backpack plus the work of the climber. So I'll add my answer from part A. And remember, a newton times a meter is a joule. 964 joules plus 4920 joules. So I get 5884 joules as my answer for the total work. And then the last part, part C, says during the 30 minutes, what is the climber's average power in kilowatts? So today we learned that power is equal to the work divided by time. So this is going to be the total work, which I just found, 5884 joules over, and luckily I've already done my conversion to seconds, over 1800 seconds. Now when I look at my unit, a joule per second is a watt, named after James Watt, and then 5884 divided by 1800 ends up being 3.26. So 3.26 watts. So the only new thing we did today was learn that powers work over time. And then if we want to convert this to kilowatts, kilo means 10 to the third power, so we would move our decimal point over. So, and if I did two significant figures, 3.3 times 10 to the negative 3 kilowatts. And because a watt is so small, most of the time power is expressed in kilowatts, because just watts are so tiny. And that's it.